Hello everyone, I'm Shixing Song, a third-year PhD student from MIT, advised by Professor Menjia Ye. Today, I'm going to present our work, Oreo Protecting ASR Against Microarchitectural Attacks. This work is done by Menjia, Joseph Zhang, and me. So, at high level, Oreo is a software-hardware co-design mitigation that strengthens ASR against microarchitectural attacks. As we all know, ASR is a widely deployed software security mechanism that relocates the victim program, the blue box, with a random offset and hides its actual address from the attacker. However, in the current existing virtual physical memory interface, the ASR secret is threaded through all the page tables and microarchitecture structures such as caches, TLBs, BTBs. This causes ASR exposed to a very large attack surface. Oreo can solve this problem. Oreo introduced a new layer called the mask memory, sitting between the virtual and the physical memory. It first maps to the virtual memory to the mask memory by redacting the ASR secret inside the virtual address. Then, it uses the secret-independent mask addresses to access all the page tables and other microarchitecture structures, thereby blocking all the side channels. So, why do we need ASR in the very first place? Consider a very classic code reuse attack. The attacker aims to override a victim pointer, the blue block, to redirect its control flow to some sensitive code. For example, assign the attacker itself the root access. ASR relocates the victim program by a secret random offset. After doing this, the address of the sensitive code is randomized and hidden from the attacker. If the attacker still performs the same control flow redirection, it will end up with jumping to an invalid target and cause a crash. To avoid the crash, the attacker has to perform an extra step to guess the secret, and then, which means that ASR successfully increases a barrier against the code reuse attacks. It is widely deployed in modern systems such as Linux, Windows, and Mac OS. So, why ASR is vulnerable to so many, However, bypassing ASR becomes extremely easy with microarchitecture side channel attacks. Here I'm only listing a subset of attacks that has demonstrated successfully leaking the ASR secret. More importantly, these attacks not only stay in the research papers, it is actually also used by the real-world attackers. Here is a document by the Google Zero project. In this document, they demonstrate that they can bypass ASR with the prefetch attack and then corrupt the kernel stack. In the same document, they conclude that kernel ASR is comprehensively compromised on x86 against local attackers, and has been for the past several years and will be for the indefinite future. So why ASR is so vulnerable to all these microarchitecture channel attacks? I'm going to explain why using two concrete attack examples. The first example, the attacker aims to leak the kernel ASR secret from user space by exploiting the ASR-dependent address translation. In this diagram, the victim kernel code is relocated by a secret, as shown in this figure. All the attacker needs to do is already shown in the yellow box. You can see it's very simple. So how come is it possible? First, when the attacker triggers a system call, the processor will jump to the randomized virtual address. Here we highlight the randomized digits 21 with red. During the address translation procedure, the secret randomized digits 21 will be used to index into page tables, usually the second and third level page tables. You can see that the hex 21st entry marked by green is accessed during the address translation procedure. Then, the processor will cache this corresponding page table entry inside the cache and cause secret-dependent side effects on the cache. Therefore, the secret is spread through over the page tables and all the memory system, exposing a very large attack surface. In a word, ASR secret is used to index into page tables and microarchitecture structures such as cache, TLB, and BTBs, thereby leaking easily. Alternatively, ASR can also be leaked by the attacker distinguishing the valid and invalid addresses. Here is an attack gadget. First, the attacker pick an address by guessing the secret digits. Then, it probes each guest address for 2 times, and then measure the latency of the second probe. Usually, the attacker will use transient probe so that it can suppress the crashes by accessing an invalid address. For example, the DRK attack, they're using the Intel transactional synchronization extension to suppress a crash. When the attacker probes a valid address, at the first probe, the processor will insert an entry to TLB. As a result, the second probe will encounter TLB hit and spend less time. However, when probing an invalid address, the address translation will not be cached in the TLB, so the second probe will take longer time. Therefore, the ASLR secret is leaked because accessing valid and invalid addresses has distinguishable microarchitectural side effects. So far, we are already saying that the ASLR secret is leaked through many microarchitectural side channels because, first, the ASLR secret is used to index page tables and other microarchitectural structures. Second, accessing valid and invalid addresses has distinguishable microarchitectural side effects. Our goal in this project is to make ASLR secret bits microarchitectural independent. The key point of achieving this goal is to make sure that the bit is not used to index into the structures, and accessing valid and invalid address has indistinguishable microarchitectural side effects. Now let me show you how we achieve this goal in our project. The key component of Oreo, as I already mentioned, is a new memory interface. On top of the virtual physical memory interface, we introduce a new layer called the mask memory. We first divide the virtual memory into many subregions. Due to ASLR, only one of these subregions actually contains the valid code block. Then we map all these subregions, no matter whether they contain the valid code or not, to the same region inside the mask memory. By doing this, all virtual addresses that are only different at the randomized base are actually mapped to the same mask address. Here, the randomized address FF21ABC and other invalid ones such as FF00ABC are all mapped to the same mask address, FF00ABC. By doing this, we redact the secret bits in the virtual address and create a secret independent mask address space. We then use page tables to map the mask memory to the physical memory. We also use unused bits in the page tables to store the secret ASLR secret bits. We also store the secret bits inside TLB. Very important thing to note here is that although we store the secret digits in the page table entry, the location of the page table entry stays secret independent. Therefore, the secret digits is not used to decide which entries in the cache is used to cache the page table. Therefore, we successfully blocked the first attack. In summary, the key insight of Oreo is that it uses secret independent mask addresses in page table work. Now, let me demonstrate to you how Oreo maintains the same ASLR security check without leaving microarchitecture dependent side effects. Here we are showing the lifetime of instruction in an out-of-order processor, where we're showing some transient stages such as fetch and execute, as well as a non-transient commit stage. In the baseline, whether a fetch PC is valid or not is actually affecting the transient stage behavior. For example, as we recall the second attack. When probing valid and invalid address, the processor behaves differently, and only the translation for valid address inserted into TLB, so reprobing the valid address has a shorter latency than reprobing the invalid ones. With Oreo, we always use masked addresses, which are secret independent in the transient stages. We also delay the security check against these ASLR security bits to the commit stage. By doing this, we ensure that in the transient stages, probing valid and invalid addresses always has indistinguishable microarchitecture side effects. And we also make sure that the attacker can only distinguish valid and invalid addresses at the commit stage, where actually when you access the invalid address, you will always cause a crash. Note that the ASLR secret bits are regenerated after the crash, so this attack is not effective anymore. Another thing worth noting is that here, we only delay the security check, while other operations such as fetch, load store are not delayed at all. Therefore, Oreo does not introduce extra performance overhead on the pipeline. However, you see that Oreo sounds very perfect so far, but we're actually facing a security dilemma. Consider a Spectre attack, where the Spectre aims to execute the Spectre gadget inside the memory speculatively. In the baseline, The attacker first needs to leak the secret digits of the spectral gadget address and then speculatively execute it. However, with Oreo, the attacker can speculatively jump to the address with any possible randomized digits and achieve the same goal. In other words, making valid addresses and invalid addresses indistinguishable indeed makes the spectral attacks easier. Now let me dive into this dilemma to deep analyze how the trade-off between protect and not protecting these secret bits. Consider virtual address with specific bits randomized by ASLR. We're going to analyze the pros and cons of protecting and not protecting these bits. We call the protected bits Oreo bits and the unprotected ones baseline bits. If we do not protect all the randomized bits, the system has no resilience against this ASLR bypasses. Therefore, it is vulnerable to code reuse attacks. If we apply Oreo to protect all the bits, the spectral attack can proceed without any ASLR bypasses, therefore make the system more vulnerable to spectral-like attacks. Therefore, the best option is to only apply Oreo to protect part of the bits, and we can be safe on both sides. Actually, this setup is compatible with current Linux setup. Here is how we achieve this goal. In the baseline, the kernel ASLR randomizes bits below 29. We find that we can actually use large unused region in the kernel space to randomize more bits up to bits 38. We can then use Oreo to protect these extra randomized digits without affecting the system's original resistance against spectral-like attacks. For user space ASLR, most of the virtual address bits are already randomized by baseline. So how can we deal with this case? We actually find that there are existing some non-canonical bits in the address that serve our goal pretty well. So here is our setup for Oreo on user space ASLR. So before I switch to my evaluation, I want to mention that there are more details in our paper, like the prototype, where we implement software changes on Linux and hardware changes on Gen 5. We also perform our performance evaluation on spec and LE bench, and also security evaluations on multiple leakage passes. Furthermore, we also include a formal reasoning of Oreo security property in an extended version of our paper, which is on archive. Here is the performance evaluation result on spec benchmark, where we measure the cycle per instruction performance with and without Oreo on the spec benchmarks. As you can see in the diagram, Oreo introduces negligible performance overhead on all benchmarks. On average, overhead is 0.11%. We then perform a security evaluation using an attack example, the profession attack. On the baseline, profession from the valid address takes shorter latency than the invalid address, because only the valid address has the translation information stored in TLB. On the other hand, with Oreo, profession valid and invalid addresses has the same latency. Thereby, the profession attack no longer works with Oreo. In summary, in our work, we demonstrated that ASLR is vulnerable to many microarchitecture side channel attacks, and we show that by proposing this 3-layer virtual memory interface by adding the mask memory in between, we can successfully block all these microarchitecture side channel attacks. That's all for my presentation, and I'm ready to take any questions. Thank you.
Hi, cool work, George Washington University. So for the user space Oreo bits, how do you solve the backward compatibility issues with the unchanged code?
Oh, so
a few more slides earlier. You have several, yes, here. It's 5 bits. When it interacts with the legacy code, how do you solve the compatibility issue?
So first, most user programs, if they are compatible with ASLR, they're written with position, compiled with position independent code.
No, I mean, you store these bits in this virtual address, right?
So you already randomize the virtual address. The virtual address, there are 64 bits in virtual addresses, but the current systems, they only use the lower, 48 or 52 virtual address bits, depending on the current system configuration. But higher bits are always 0 or always 1.
Is this a virtual address, this entire?
Yeah, this is a virtual address.
Then when you dereference this address, it needs to be canonical, right?
We change the kernels, we change the software and hardware that when you dereference address, it will extract the secret bits and
Yeah.
So you don't make it, it hasn't to be canonical.
Okay, so did you use any legacy library? Say, when you use this virtual address, you need to clear this first few bits and pass this canonical address to the library to use. And when this library returns a raw pointer to you, how do you kind of recover this Oreo bits? Are they all the same? This is a compatibility issue with unchanged code, unless you change everything, the whole software stack.
I think
Okay, we can talk more offline.
yes, but I want to mention the user program can be relocated and randomize the non-canonical addresses when you load the user program into memory. So it is already relocated by the position independent code related features. And the next question.
Hi, I'm Tim from University of California, Irvine. Thanks for the talk. So since you're adding one more layer of indirection, you would imagine that it would add some overhead to it, right? But I saw that on some benchmarks, it actually speed up the runtime. So do you have any explanation on why is that happening?
Okay, you can interpret this new extra operation in two aspects. First, this extra operation is just redacting the secret bits from the addresses, which is a very simple combinational logic, and which will not add much extra latency on the pipeline like critical path. So it will not. We do not introduce extra delays or cycles on the pipeline. And when you talk about a small difference on running with and without Oreos, this difference might be caused by some noises on running benchmarks for different times, and also we're somehow using different cache entries, which will have some subtle performance difference. But that will not cause critical delay or performance overhead. Does that sound good to you?
Yeah.
Okay, thank you.
Okay, let's thank the speaker one more time.